When calcium carbonate is added to dilute hydrochloric acid, carbon dioxide gas is released. So simple experiment, simple chemical reaction we've seen. Which set of apparatus are suitable together with a stopwatch for the following rate of this reaction? Okay, so we've discussed this a bit, and this is one of the ways you can actually measure the rate of reaction. The loss in mass can be plotted on a graph, and you'd get something like this, and you can figure out the rate of reaction even though you're not an artist in drawing graphs. Okay. For the second one, you can also collect the gas evolved, and for every minute you can measure the volume and essentially have a graph, something similar but the inverse because you're now collecting it, right? Something like that, and you can figure out the rate. In the last one, the gas will escape the Cecil funnel and won't be collected over here. So only 1 and 2 are possible setups that allow you to measure the rate of reaction. So the correct answer is B. This question repeats a lot. The graph divides melting points of lead and tin. So you see, this is the melting point of lead, and this is the melting point of tin. So when you have pure lead with 0% tin in the mixture, it's close to 330, 320 degrees Celsius. And when you start adding tin, it becomes lower, and what's interesting is it actually becomes way lower than both their melting points, which is weird to think about. Then you add more tin, it starts rising until it matches the tin's melting point. At 100% tin, you have 0 lead in there, right? The graph shows that the mixture of lead and tin must have melting points that is above that of tin. Actually, you do get lower than that of tin. Below that of lead, well, that's true because you can't have a boiling point according to this graph higher than that of lead. So B looks correct. Below that of both tin and lead, that's incorrect. It does get higher than tin. Between, no, it does get lower than tin, right? Looking at the graph, the question is pretty straightforward. The graph was like telling you that it was a very complicated question, but it's a straightforward question. A Buckminster fullerene has a chemical formula of 60 carbon atoms because there's 60 carbon atoms joined together in the shape of a football. So this is exactly how, a football arranges itself. It's like a pentagon with hexagons all around it. Gives it that curve it needs to turn into a ball. How is the structure of Buckminster fullerene best described? I'd say a football, but let's see. A covalent compound? It is a covalent compound, that's true. An ionic? No. This is all covalently bonded, and 2 Buckminster fullerenes, if there was another one, would behave very similar to that of a simple covalent structure like water, let's say. So Buckminster fullerene, if you have a sample of it, it's liquid at room temperature. That should automatically tell you what sort of what type of structure it is. It's a simple covalent structure, even though there's 60 atoms, right? A polymer? It's not a polymer. And molecular? It is a molecule. So I think between A, that could imply that it could also be giant covalent, and it's not giant covalent, right? Because it's a liquid at room temperature for one thing. So it has to be molecular. That's what they're going for. Looking at the marking scheme, it says the trick was compound. It's not a compound, it's a pure element, right? It's an allotrope of carbon, so to speak. So that was why A was out, and yeah, okay. Stupid question. In an experiment, 1 centimeter of gas, hydrocarbon Z, requires 4 centimeter of oxygen to complete combustion of 3 carbon dioxide, 3 centimeter cube of carbon dioxide. So element, or not element, and this hydrocarbon X can react with oxygen to form, it should react with 4 bits of oxygen, 4 pieces of oxygen to produce 3 carbon dioxide and, water, of course. So if you gotta produce 3 carbon dioxide molecules, you gotta have 3 carbons. So with that in mind, C and D are one of your options. Looking at C, if we try to balance it out, if we try to burn it, let's burn it in green. C3H4 should give us the right answer. Reacting with oxygen to produce 3 molecules of carbon dioxide and some hydrogen. How much hydrogen will it produce? 2, because there's a 4 over here balancing it out. How many oxygens do we have? We have 6 over here, 2 over here. Total of 8. Now we have a total of 8 on the left-hand side as well. That's balanced, and this is what we needed. 4, 3 for every one of this. Oops. One of this. Right? So the correct answer is C. Which reaction is not a redox reaction? Taking a closer look at calcium over here. Looks like this is not a redox reaction because calcium and carbonate is calcium 2 plus, which is turning into still calcium 2 plus because it's bonded with an oxygen with a minus sign on it. Anyway, all group 2 elements will only have 2 plus signs on them anyway. Right? This has a charge of 0 on it, and this will have a charge of, I guess, positive 2 on it, on this carbon. It's definitely something. It's not 0 anymore, right? Like, it's hard to figure out for these compounds because we don't really do them. And carbon having a positive 2 doesn't really make sense. But, yeah. Okay. Similarly, over here, this is also redox because pure element is turning into a compound. So, definitely some stuff going on over here. This is actually the equation. The last one is the reduction of carbon. This is the process how you extract iron, right, from rust, from hematite. So this would be your hematite. Fun fact, hem means iron in Latin. Hematite, that's why it's hematite or hemoglobin, right? And yeah, that's reduction. So our first answer was A. Aqueous copper sulfate solution is placed in an iron container and left to stand for several days. The statement describes the reaction. So it's in an iron container, which is going to be pure iron, which reacts with copper sulfate, CuSO4. Now, what sort of reaction will take place here? Iron, being a more reactive metal, will be able to displace this copper. It's a displacement reaction going on. What's going to happen is it's going to turn into iron sulfate and produce copper. So let's see what description best describes it, or whatever these options are. Atmospheric oxygen reacts with copper sulfate to give black copper oxide. I mean, no. Some fine iron particles are formed in the solution. They would, but this is actually aqueous. So it will be not fine particles. Part of the container in contact with the solution is coated with copper. That's true, right? It's gonna be coated with copper. The solution turns from green to blue. Actually, the reverse, because copper sulfate is blue in color. And that's going to be green in color because it's iron. It's either red or green, right? So it's going to turn from green to blue. So the correct answer is C. Okay, C is the correct answer.